Example 6 is our first example that asks us to find an orthogonal diagonalization of a matrix. So we're given this matrix 3, 1, 1, 3, and this is the same matrix from example 4, so we already know the eigenvalues and eigenvectors from that example. So finding the eigenvalues and eigenvectors are steps 1 and 2, except in step 2 we also have to find unit eigenvectors. So what we're going to do is just choose any eigenvector. So in this case for x1 we're going to choose the vector -1, 1 and normalize it. So we can see that the norm of this would be square root of 1 squared plus 1 squared would be square root of 2, which would also be the norm of x2. If we take x2 to be 1, 1, its norm would also be square root of 2. So we normalize them, and we're going to call these normalized vectors p. So p1, and that would be -1 over root 2, +1 over root 2, and p2 would be 1 over root 2, 1 over root 2. Okay, then we go up above and we see what step 3 is. It says for each eigenvalue of multiplicity k greater than or equal to 2. Well, there were no eigenvalues with multiplicity 2 or greater. They're all just multiplicity 1. So step 3 we can just go directly to step 4. So step 4, just take all the p vectors that we found in steps 2 and 3 and use them as columns to create my p matrix. So -1 over root 2, 1 over root 2 is the first column in the p matrix, and then p2 is the second column. 1 over root 2, 1 over root 2. And then it says to verify that p transpose AP gives you the proper diagonal form. So p transpose, if I take the transpose of this, I get itself. The A matrix was 3, 1, 1, 3 times the P matrix and if I multiply all those out I should get a diagonal matrix, and not just any diagonal matrix but the diagonal matrix with the 2 original eigenvalues down the main diagonal. And since this was the first column and it corresponds to that eigenvalue, that should be the first eigenvalue we see. This is the second column, it corresponds to that eigenvalue, so that eigenvalue should appear here. So we call that the D matrix since it's diagonal.